All right. Hi, everyone. Welcome back to our seminar on optimization and real algebraic geometry. Today, we are pleased to have Jose Rodriguez from University of Wisconsin. He's going to talk about estimating Gaussian mixture using sparse polynomial moment systems. Thank you.
Okay, so this will be, let me figure out how to get this. Okay, there we go. So I won't be able to see the chat. If you have questions, feel free to spit them out loud, and I can then have a conversation as we go. So while people come in to the seminar room, one advertisement I want to give is this SciAm seminar on applied algebraic geometry. So it's a seminar I co-organized with Kathleen Cohen, Joachim Rosenthal, and myself. And our next speaker is going to be this Tuesday by Jesus De La Vera. So he'll give a wonderful talk on the geometry of the space of all pivot rules. Here's a Zoom link. I can share with you these slides and you can click on it, or you can ask for me this Zoom link at the end and then you can save it. But yeah, so it happens every second Tuesday of the month. And we've had a wonderful lineup of speakers, which if you haven't seen, you can check out their YouTube recordings. Great, so this is the SciAm saga, which I think is a great name. So today I'll talk about estimating Gaussian mixtures using sparse polynomial moment systems. So that's the title of the paper, and this is joint work with Julia Lindberg and Carlos Amendola. So Julia Lindberg is a PhD student at UW-Madison. She'll be graduating in May, and then she'll be off to MPI for a postdoc, and then at UT Austin for a postdoc after that, starting in January. Carlos is already a postdoc and will be starting a tenure track soon. And so we did this together during these COVID times. We had this paper come out. There's some related works that I will not speak on. So there's this notion of maximum likelihood estimation. And so we studied the optimization degree of that problem, where the constraints are given by sparse polynomials. So again, we see the word sparse polynomials appearing. And we have some results about this related to BKK bounds, which is of a similar flavor of what I'll talk about today. Sparse polynomial systems was a research track or some research projects I did with a postdoc who's at Notre Dame, Taylor Brejcevic, and a good friend, Frank Sotilli at Texas A&M, and his student, Thomas Yao, where we develop algorithms to study sparse polynomial systems. I hear Botong is in town at Purdue, which is nice. And I have some work with him along with Laurencio Maxim, where we study Euclidean distance degrees from a topological viewpoint. And we have some idea of understanding these degrees using algebraic topology, which allows us to give stopping criteria for some numerical algebraic geometry algorithms, which I'm interested in. Okay, so that's a bit of a background and history while people get settled in to the Zoom room. So the outline of the talk, I'll tell you a little bit about how I think the data and to motivate the method of moments. Then we'll talk about why we like solving polynomial systems, which maybe I don't have to convince this audience, but it's always good to, I don't know, carry the flag of applied algebraic geometry. And we'll see a little bit about Bezout and Bernstein's theorems and how the ideas for the proof of Bezout's theorem using Bernstein's theorem motivates some of the proof techniques we use in our project. Okay, so with that, let's begin. So we'll start off with Gaussian distribution. And so this is a type of continuous probability distribution for some random variable. And so you could describe this density by a density function here. F of x is equal to 1 over sigma squared root of 2 pi times an exponential with stuff up here. So if you were to integrate this function from minus infinity to infinity, you'll get 1. And so here are some pictures of Gaussian distributions for choices of mu and sigma squared. So somebody gives you the mu, gives you a sigma, then this specifies your density. So what do these mean? In statistics language, these are parameters. And so mu is the mean and it measures the center of your density. Sigma is known as the standard deviation and it measures how spread out you are. The variance of the distribution is sigma squared. And so these I'll constantly interchange. If you know one, then you know the other. So what's our data? So maybe somebody gives you 100 samples from some density. So here we have 100 samples from a density. And in fact, these are taken from a Gaussian distribution with mean 50 and standard deviation 15. These are centered. Okay. So one way you could think of this, maybe heights of high schoolers, or pick your favorite random variable. You can think of this. And so for those of you that haven't seen this before, there's a Stat 101 fact called the 68, 95, 99.7 rule. So this is an empirical rule. And it says that, for example, 68.27-ish% of the values will lie within one standard deviation of your mean. So in terms of this data here, this says that 68 of these numbers, around 68 of these numbers will be between 15 and 65, or sorry, 35 and 65. Why these numbers? Because one standard deviation is 15, the mu is 50. So we expect, using this rule, 68 of these numbers lie between this range. Okay, so this gives you some sense of how to think about the data if you haven't seen this before. And as usual, feel free to interrupt me, shout it out, and we can address questions or comments during the talk. Okay. So what's another way that, what's a way that we can get an understanding of our distribution? And one way to do this is by looking at moments. And so what we do is instead of integrating our density from minus infinity to infinity, in which case we would get 1 because it's the density, we could integrate x times f of x. And this is known as the first moment. And if you were to do this for the Gaussian distribution, you would get mu. And what you see here is that this is a polynomial in the parameters in the statistics sense. So this is a polynomial, the mu and sigma squared. All right, you could do it again for this to get the second moment. So you look at x squared times f of x, you integrate, and you'll get mu squared plus sigma squared. Well, why should we stop at 2? Let's keep going. You could do the third moment, and you would get this here. So in general, if you could look at the rth moment, you look at the integral of x to the r times f of x, and there's some recursive formulas that express this moment in terms of polynomials of mu and sigma squared. Right, so that's on working with our density itself. We could extract these polynomials. On the other hand, we were given this data. So we don't, in practice, we don't know what this density is, but what we do know is we have some data. And so what we could do is try to get a handle on the density by considering empirical moments. So what do? The first empirical moment would just be taking the average of all of our samples. In general, you could look at the rth empirical moment. And so this takes each of the numbers we saw on the previous slide, raises it to the rth power, and then averages out to get the empirical moment. So in the previous example, the first empirical moment would be 48.62, and the second empirical moment would be 2,601.64-ish. Now, in Stat 101, yes, maybe in the middle of the semester, you start talking about what's known as the method of moments. That should be a blue S, sorry. So you're given these empirical moments, which are extracted from the data. And then what you do is you solve a system of polynomial equations. So you solve which polynomials? Well, you take your first empirical moment, and then you subtract from it your first moment. So that's this m1 minus mu, and you want this to be equal to 0. You do this again for your second empirical moment, and then your second moment coming from the densities, and you want this to be equal to 0. All right, so that's the method of moments, solving polynomial systems. Now this is straightforward to do, right? I mean, once you have m1, you immediately have the mean, so that you take that as that estimate, then you plug in and you can recover the sigma squared, right? So the solution for our method of moments would be, for our particular choice of data on the previous slide, would be given by here. So this would be your estimate for the density. And let's recall what the true distribution was. The truth was mean 50 and standard deviation 15. So, you know, we're in the ballpark using this method. Okay, so that's for Gaussian distributions. Feel free to protest or comment if you have questions or concerns, but if not, I'll keep on going. So as we've learned these past couple of years in these COVID times, the world is not normal, but in fact, it's a mixture. And so, for example, instead of a Gaussian distribution, we have, let's say, a mixture of Gaussians. So you take some convex combination of a pair of Gaussians, and this gets you a new density. So for example, you might think of this as unvaccinated people, and there's some mixture parameter lambda that put all these people in the world together. Or maybe you're in a classroom setting and you have students that are doing their homework, students that are not doing the homework, and these two populations are likely to have different behavior, or these two different population students might have different behaviors. But because we don't spy on our students, we don't know what this underlying mixture is. Okay, so questions and goals. What are the moment systems arising from Gaussian mixtures? And the second thing, and more importantly, what can we devise methods to solve these moment systems, as we saw over here? So this one is trivial to solve, but in general, these moment systems can be highly nonlinear and very complicated. All right, so I know people have to run off at some point in time, so let me state the results and outline. So our main results is to consider mixtures of univariate Gaussians, and we derive a binomial system that provably finds all solutions to the moment system. So as a corollary, we're able to do method of moments for these mixtures of Gaussians. After, I want to tell you some sparse polynomial system background, and time permitting, to tell you how our results in the univariate case lead us to develop methods to study mixtures of high dimensional Gaussians. So here we had one variable, but we could work in hundreds of thousands of variables as a consequence of our univariate results. So let's quickly do an undergraduate review. So what does solve mean? So if we had a quadratic polynomial, we could get this formula to express our roots in a closed form. Same with the cubic and quartic polynomials. But quintic polynomials, we know no such formula exists by Galois theory and Abel's theorem. But the fundamental theorem of algebra tells us that the number of roots is determined by the degree of the polynomial, so long as we count multiplicities appropriately. And so what we do is we can numerically approximate all of these roots. So if I'm given this degree 5 polynomial, what I can do is extract numerical approximations of the roots. So I can then see which ones are real and which ones are complex valued. So in the statistics problem, we're only going to be interested in real solutions, and often only a subset of the real solutions, because only a subset are going to be statistically meaningful. And if we have these numerical approximations, we can actually pick out the real solutions, which is one advantage for our methods. So let's set the stage. To attack our problem, we want to have a two-step procedure. First, we want to count the number of solutions to our moment system, or at least bound the number of solutions to our moment system. And then second, we want to find all the solutions. And once we find all the solutions, we could pick out our favorite one to be an estimate for the method of moments. Why do we solve? Well, there's a whole community on why we solve. There's this SIAM algebraic geometry community, and I'm sure some of you have organized special sessions at this conference. And yeah, so there's like 40 of them just listed here, and there's a long history of this conference bringing out new collaborations and new research directions. So what do I mean by a sparse polynomial system? So I want to keep things light and consider just the bivariate case. So I have two unknowns, but the idea is in the two unknown case, generalized to the arbitrary number of unknowns. So a polynomial is called sparse if a priori we know which monomials appear with non-zero coefficients. So here's a bivariate polynomial and two unknowns, for example, where these a's are all non-zero, let's say. Now, the total degree of our polynomial f is the maximum of the sum of the entries of the exponent vectors. So it's the maximum of these integers here. And so the standard thing that you learn in algebraic geometry is Bezout's theorem, is that this gives you an upper bound to the number of solutions of a square polynomial system. So if I have a polynomial system consisting of two equations and two unknowns, then I know it has at most degree g times degree h solutions, where g and h are my polynomials. And let's assume I know there are only finitely many solutions. Okay, so this addresses our step one goal of counting solutions to a polynomial system, because the Bezout bound can be tight or is tight generically. So for example, this polynomial system has a tight Bezout bound. Okay, this can be viewed geometrically. So if we're given the polynomial g, this might be a circle, and then, or its variety is then a circle. H would then be some ellipse, and then we expect to see 4 points of intersection. Over here, we also see 4 points of intersection if we can view over the complex numbers, but we still count them even though we can't see them. Okay, so but we want to do better than Bezout. And well, why? Because Bezout can be a pretty bad bound. And so, for example, in this polynomial system, we see that the Bezout bound is d squared. But in general, we don't have d squared solutions. So maybe some audience participation. Does somebody, can you shout out how many solutions this system has? I don't hear any shout outs. So geometric hint, here is the case where d is equal to 2.
D solutions.
D solutions, there we go. So in general, this system has D solutions. You can see it by doing some clever substitutions. A remark on genericity. Genericity just means if we perturb the coefficients, then you have the same number of solutions. So here is an example of a non-generic system because you don't have any solutions. All right, so the goal is, after specifying the monomial support, give a bound on the number of solutions to a bivariate polynomial system. And this is done by Bernstein's theorem. So the number of isolated solutions in the algebraic torus is bounded above by the mixed area. So I haven't told you what mixed area is. We'll give an example on the previous slide to illustrate the idea. And this bound is a tight if the coefficients are generic. So an example of mixed area, recall we have our polynomial f, and we can then find its Newton polytope, or Newton polygon in this bivariate case, where we look at the convex hull of the exponent vectors. The mixed area of two polytopes, P and Q, is then the area of their Minkowski sum with their individual areas subtracted off. So for example, if G is this polynomial here and H is this polynomial here, then the Newton polytopes are going to be a square and a triangle respectively. Their Minkowski sum would be this figure here. You take a vector in the triangle and a vector in the square and add them up for every possible pair of vectors in the triangle and square, and this gives you the Minkowski sum. The mixed area then is going to be 4, and that's the area of these parallelograms. So this is in contrast to the Bezout bound, which is 6. So the Bernstein's bound tells us this system will have 4 solutions in the algebraic torus, whereas BKK tells us there's 6. So classic results is by Huber and Sternfels that tell you how to develop what's called a polyhedral homotopy method to find these solutions to the polynomial system. And lots of work has been done on both on the theory and software side. Yesterday there was this week is JMM, and yesterday there was a session organized by Taylor and Frank, where a lot of the talks mentioned these BKK bounds and how they are used in applications. And we're seeing a hint of this in a second. So mixed area has an important property, namely monotonicity. So what this says is that if you looked at two subpolytopes of P and Q and looked at their mixed volume, then this is going to be less than or equal to what you started with. So the idea is that if you were to kill off terms from your polynomial system so that you have a smaller support, then you could have fewer solutions in algebraic torus. Okay, so let's do an example with binomial systems and mixed areas. What we want are solutions with non-zero coordinates, and that's what I mean by solutions in the algebraic torus. And so because solutions have non-zero coordinates, it makes sense for us to consider Laurent monomials where the exponents are negative. So if we're given this binomial, we can simplify it so that we have this, like all the variables on one side and one on the other side. So if we want to solve a binomial system in two variables, it suffices to consider systems that look like this. So question, well, first question, what are the Newton polytopes? And the Newton polytopes are going to be line segments because, well, you're looking at the convex hull of a pair of points, which gives you a line, or it gives you a line segment. And it turns out, if you think about it for a second, then the mixed area of the Newton polytopes of these pair of polynomials is going to be the determinant of their exponents in a 2x2 matrix. Right, so one example, if you had an upper triangular system, then it's very easy to solve because you can back substitute. You can solve for the y, back substitute, and then get the x. So in general, there's this notion of Hermite normal form that allows you to simplify your given binomial system so that you can put it in this nice form over here where you can solve via back substitution. And so here's an example of this in this small example. So Hermite normal form tells you there exists some matrix over here where if you multiply your exponent, this matrix of exponents, you can then get this upper triangular matrix whose corresponds to exponent vectors as seen here. And these systems have the same solutions. So you can go from this complicated system to this triangular system. And this idea works for arbitrary number of unknowns for binomial systems. Okay, the point is that binomial systems easy to solve. Okay, so now geometric idea. How do we get the Bezout bound from the BKK bounds? And so here's a proof by picture. If G and H are two general degree D polynomials, then their Newton polytopes are triangles, as seen here and here. And their Minkowski sum would be this larger triangle, and thus their mixed volume or their mixed area would be the product of the degrees. So we in fact see this Bezout bound from the BKK, or from this Bernstein's theorem, sorry. So note that this rectangle that we see here is a Minkowski sum of line segments. So we have a line segment here, a line segment here, and then Minkowski sum gives us the blue rectangle. So this motivates us to consider these polynomials, x to the degree of g minus 1 and y to the degree of h minus 1. So these correspond to these line segments. And so the idea is then that we can use a continuation method where we vary t from 0 to 1 that takes our binomials to our polynomials of interest, namely g and h. So we want to solve g is equal to 0 and h equals 0. This is too tough. So what we do instead is we consider a binomial system and deform from t is equal to 0 to 1 and track solutions as illustrated in this picture here. So g here corresponds to a binomial system with 8 solutions. And as we vary t from 0 to 1, we get the 8 solutions for g and h being equal to 0. So the global picture is illustrated here. The local picture is illustrated from this picture from the Julia homotopy continuation page that uses predictor corrector methods to actually do this path tracking as illustrated in this global picture. So one path has this picture going around. Okay, so the point is that there exists off-the-shelf software that can do this tracking for us, where we take a binomial system to our target system. Okay, so here's our binomial start system lemma. So if we're given a polynomial system, G and H, which we want to solve, and if we were to pick a pair of monomials from each of these polynomials, G and H, these induce a binomial system. And if this binomial system has the same number of solutions to our target system, G and H being equal to 0, then we can just do this tracking idea and we'll find all of the solutions that we want. All right. So how does this relate to the method of moments? So let's work in our simple Stat 101 mid-semester example. So here we have a polynomial system, two unknowns. Okay, two unknowns, mu and sigma squared. We're given M1 and M2. So which binomial system do we consider? We consider M1 minus mu and M2 minus sigma squared. So we can deform this binomial system to our target system using this idea over here. Questions about this, because this is a key point and we want to expand on it in general. So I'll pause for a second.
So what is the target system?
My target system is the one that's illustrated here, this non-binomial system. Mm-hmm. My start system is I'm picking out the orange underlying terms. I'm picking out pairs of terms in this target system. And what we do then in general is, because I know you have to go in a second, is that we have more complicated moment systems. And these this idea works on these more complicated systems. And I'll say that in about 5 to 7 minutes. So let me continue on.
Sorry, I need to drop.
Yeah, no problem.
Continue.
So density estimation, as a recap, is a common problem in statistics. So for giving capital N samples from a distribution that's not known, can we estimate this distribution? And so you assume that this distribution comes from some family, and the family that we want to consider is a mixture of Gaussians. And we consider this because there's a theoretical result that says this is a universal approximator of densities. Okay, so we talked a little bit about Gaussian mixtures at the start of the talk. Here's a visualization of a Gaussian mixture where we have this Gaussian here with mean -2, this Gaussian with mean 2, and we mix them by this quantities here. Okay. So question, what are these polynomial systems that we want to solve? So we apply the same idea where we compute these integrals to get the first, second, third, fourth, and fifth moments. We get these first, second, third, fourth, and fifth moments for our density. And we see that these are polynomials, and the mixture parameter lambda, the mu and sigma of our first Gaussian, and the nu and tau of our second Gaussian. Okay, so here we have a polynomial system and 5 unknowns. Oops. Okay, so given some samples like we were given in the beginning of the talk, we could then compute the empirical moments, which are the left-hand side. And given the left-hand side, we then want to find the right-hand side. So in some sense, you can think of this as an inverse problem. So let's consider the case where k is equal to 2. We have 2 Gaussians. So if we have a mixture of 2 Gaussians, then we have these parameters, mu sigma squared, nu tau squared, and lambda being our unknowns, where this lambda does the mixing as seen here. The moment system is as we saw before, and we see this left-hand side is the given. Now, Pearson back in the day reduced this to a univariate degree 9 polynomial in the product of the means. And so if you were to plug this into your favorite polynomial system solver, you'll get 18 solutions. And Pearson's motivation came from studying the Naples crab populations, and there were 2 subpopulations. And this picture is from this work here, where Carlos Amendola, John Charles, and Bernd studied Gaussian mixtures. Okay. Okay. So how does this relate to what we're doing? And so instead of considering the problem where the mixing coefficient is unknown, I want to assume I know the mixing coefficients. And now we could debate philosophically if we think that this is a good model or not, but this is a model that's often used in practice where you know the mixing coefficients. And so if you know the mixing coefficients, then you have a system of 1, 2, 3, 4 equations with 4 unknowns. So the 4 unknowns are mu1 and sigma1, and mu2 and sigma2. So these are the means of the two populations and variances. So we want to solve this polynomial system. And what we do is, as a step 1, we bound the number of solutions. And one way to bound this is to pick out these pairs of terms from each polynomial and find the mixed volume of the associated binomial system. And it turns out that the mixed volume of the binomial system is equal to the mixed volume of the entire system. They're both equal to 6. Okay, so then what can we do? We can use a continuation method where we look at this binomial system to get these 4 equations that are binomials. We can solve these and get some start solutions, namely these 6 start solutions, and we deform these binomials from t is equal to 0 to t is equal to 1 to solve these original equations of interest. So why do we know this works? You just apply the binomial start system lemma from this BKK to Bernstein idea. Sorry, BKK to Bezout idea. Right? Very good. Okay, so this is an example where it works for these known mixing coefficients, and we're mixing 2 Gaussians. Our main result, or one of our main results, is that this idea works for arbitrary number of mixtures. So we prove the number of solutions to this moment system with known mixing coefficients is equal to this quantity here. So when k is equal to 1, then you don't have any mixtures, and then our formula says we have 1 solution, so that's good. If we have 2 mixtures, we get our 6 that we saw on the previous slide. If you have 3 mixtures, you have 90 solutions, and so on. So how we go about doing this is we show that the mixed volume of the system is actually counting the number of solutions. And to go about doing this, we use Bernstein's other theorem, which considers initial systems and allows you to prove that the mixed volume is actually a tight bound. Okay, so as a corollary, and as hinted on the previous slide, what we have is an optimal homotopy in the sense of the number of paths tracked for density estimation in this instance, using a binomial start system. So how does this binomial choice work? Well, it's as I hinted before, you choose, well, okay, you can stare at this for a minute. I don't have time to go into detail about it, but how you might guess we constructed these binomials is how it works in general. Okay, so we didn't just focus on this unique case where the mixing coefficients were known. We also considered some other variants that appear in the literature. And these other variants gave you different number of solutions to these moment systems. And we prove that the mixed volume is tight, or at least we determine the upper bound using the mixed volume. All right, so in my last 5 minutes, let me consider Gaussian mixtures in high dimensions. And so everything I've talked about so far, we had the one-dimensional univariate Gaussians. Now we consider a random vector. So here is a random 2 vector. And so it's centered at the origin, and then its spread is now determined by a covariance matrix. So in this case, it's the 2 by 2 positive semi-definite matrix. So you can play the same game now for this multivariate setting, where now instead of integrating x to some power, you integrate a monomial into some monomial times your density. And if you were to do this, you would get these moments on the right-hand side for various choices of monomials. So question now becomes, well, which moment should you use? Amendola, Ranestad, and Sternfels give some hints on how to do this. But the key observation that we notice is that if you stare at these a little bit, you see that these orange moments here look a bit familiar. These look exactly like our univariate case. So the key observation is that if you start with the univariate case, you can work your way up to the high dimensional case. So density estimation in this high dimensional setting becomes multiple instances of this one-dimensional problem. So the idea of our result is that the method is that we have a method for density estimation for Gaussian mixtures with few components and large number of dimensions. Oops. So here are the computational results that we have. So what we do is we perform the method of moments on the mixtures of, actually it should be 3 Gaussians in n-dimensional space using capital N samples. And so for this experiment, we assume the covariance matrix is diagonal. And so in this 3 mixture setting, we have 3 times 2n plus 1 unknowns. Okay, so we have we have n unknowns coming from the mean, so where we center the Gaussian, and then we have n unknowns coming from the spread. The plus 1 then comes from the mixture parameter. Okay, so then our computational results then consider little n dimensional space. So here we see that we have 10 dimensional space, and we're able to do this in 4.71 seconds. So we're able to solve this highly nonlinear polynomial system of equations in 4.71 seconds using our method. We can go kick this all the way up to now 100,000 dimensional space, which corresponds to hundreds of thousands of unknowns, and we're able to solve this in about 8,000 seconds, around on the order of minutes. And so, okay, well, depending if you're a practitioner or a theoretical person, maybe you don't care about the exact amount of timing, but what you should care about is that this appears to scale linearly in the dimension n. So that's a nice consequence that we're not observing a curse of dimensionality if we fix the number of mixtures to be small. So I have a minute left. So in my last minute, I want to give an advertisement to this MC workshop that I'm co-organizing with these wonderful people here. This will be at Chicago, fall 23. So you should definitely make an appearance to one of the several workshops that we'll be having. First workshop is an intro to algebraic statistics. There'll be then follow-up workshops on ecological and biological systems, economics, and the last workshop will be new directions in algebraic statistics, tentatively looking at statistical learning, neural networks, and Bayesian statistics, but this is still being up for debate. So with that in mind, thank you so much. Here's some references selectively chosen for applications of algebraic geometry and some pictures associated to them. So with that, I'll finish right on time. Thank you.
Thank you. Let's thank Jose for this wonderful talk. So any question from the audience? So I have one question. Can you come back to the computation of the number of solutions, if I'm not mistaken? So do we compute the number of points or we derive bounds? So I was kind of confused.
In the high dimension or the lower, or the one-dimensional case?
In one dimension, I guess in one dimension. Or in, yeah.
In one dimension, oh my goodness. There we go. In one dimension, in this setting here, we do both. We give a bound, and the bound is the BKK bound. And we do more, we show the bound is tight.
Oh, so I'm actually asking about the Newton polygon, because in your previous slide, you were using the idea of Minkowski sum of the Newton polygons from two bivariate polynomials. So I'm actually asking for this. Maybe I didn't ask the question right.
Okay, so for the bivariate case, I showed you how to give a bound. Okay, BKK and so Bernstein's theorem gave a bound of the polynomial system using these Newton polygons. Now in this but four variable case, you would now have these four-dimensional polytopes, and you would have some more complicated inclusion formula that would give you a bound on the number of solutions to this system. All right, so that gives you an upper bound. What we then show is that, okay, this, who knows, I have no idea what these polytopes look like. Well, I have some idea, but for our purposes, we don't know what these Newton polytopes of these four systems look like. What we do know is that if we were to pick out two terms, we'd have these line segments that are contained in the polynomial, in these polygons, polytopes. And now these line segments have a mixed volume, which is determined by a determinant. And we prove that this determinant has the same mixed volume as it equals the mixed volume of the Newton polygons for these polynomials. So that's how we get accounts for the number of solutions.
All right. Thank you.
Does that help, or?
Well, I mean, for the bivariate case, my question was, then how come we don't combine the two bivariate polynomials together? I mean, or I'm wondering what happens if we treat only one bivariate polynomial by mixing them together, like g squared plus h squared equals 0. And then we have a Newton polygon, and well, maybe we get into the realm of Puzo expansions. And yeah, I'm just wondering, would that get a better bound, or do we get a better results if we only consider one bivariate polynomial by mixing them together? So because basically you're solving a system of two bivariate polynomials, right? So if instead of having g equals 0, h equals 0, if I have g squared plus h squared equals 0. Yeah, so.
I see. So it sounds like you want to consider, okay, so let's go to the bivariate case. So okay, here we're solving a bivariate polynomial system. And now if all we care about is real solutions, so then what we could do instead is, let's say, well, if I want this to be 0, one thing I could say is, let's square this left-hand side, square this right-hand side, and take their sum. So now I have one function, that's the sum of squares. And we know that, so then what do? We could, let's say, minimize it. And then if we were to, in this case, we would able to get consider this as an objective function, we could achieve the minimum by finding a root. So in what you're describing is known as the generalized method of moments. So if you have some overdetermined polynomial system, or so if you have more moments than number of unknowns, then you would expect to have no solutions if you had noisy moments. So using what you said, you could take the sum of squares, and then you could say, well, let's minimize this objective function. And this would be a different technique than the one that we're describing here. Here we're describing where we want to find the roots, or yeah, we have the correct number of equations so that we have finitely many solutions in some sense. We don't have this over-constrained case.
All right. Thank you. Any other question? All right, if not, let's thank the speaker again, and thank you all for attending our 4th seminar on optimization at real algebraic geometry. So we will hope to meet you again in 2 weeks. Thank you very much for your attendance. Have a good day.
Yeah, thank you for having me.
Thank you.
Appreciate it. How are things going otherwise, or do you have to run?
All right, let me stop the recording.